Hello, everybody. In the previous lecture, we have discussed doping, that is introduction of impurity atoms into a crystal lattice semiconductor. Those impurities are the so-called shallow impurities. And by shallow, we mean that their ionization energy is relatively low. For example, if it is a donor impurity, that is an impurity that gives away an extra electron to the crystal lattice, then when that extra electron is bound to the donor impurity, its energy level is just slightly below the conduction band energy. And for acceptor impurities, when it is in the neutral state of an acceptor impurities can be thought of as a negative ion, which with a positive hole somehow orbiting around that ion, right? So the energy of that hole is slightly above the valence band edge of the semiconductor. Okay, so they are shallow impurities. Now there are, of course, other types of impurities, such as, well, known as deep impurities. They are typically metals. The energy levels of the deep impurities are somewhere in the middle of the band gap. All right, so shallow impurities produce either electrons or holes in the crystal. In the first case, they are called donors. In the second case, they're called acceptors. Donors give away electrons. Acceptors take electrons from the valence band of the semiconductor, thereby creating holes in the valence band. The donor and acceptor doped semiconductors are said to be of N-type or P-type, respectively. All right, so not all impurity atoms are ionized. When an impurity becomes ionized, it gives away an electron or a hole to the semiconductor. So not all of them are ionized. And our immediate task is to figure out the fraction of the impurities which are actually ionized at a given temperature. The second task is to relate the concentration of ionized impurities to the concentration of electrons and holes in the semiconductor. In this lecture, I will address the first task. So for that, I will tell you I will build a simple hydrogen-like model of shallow impurities. And based on that model, we will be able to figure out the binding energy of an electron to a donor atom or of a hole to an acceptor atom. Then we will use that result to figure out the ionization energy of donors and acceptors. And finally, we will be able to write down expressions for the concentration of ionized impurities in terms of the total impurity concentration and the Fermi energy and the ionization energy of this impurity. All right, so let's start with the impurity energy levels. Let us begin with donors. A donor is an atom which has higher valence than the host lattice. So, for example, your host lattice is silicon, valence 4. Silicon has valence 4, which means that 4 electrons of each silicon atom take part in covalent chemical bonding to 4 neighboring silicon atoms. And now let's say you introduce valence 5 impurities, such as phosphorus or arsenic, into the lattice. 5 out of 5 valence electron of the impurity, 4 take part in chemical bonding, and 1 extra electron becomes loosely bound to the host atom. So what is the binding energy of that electron? You can think of a neutral impurity atom in the crystal as a hydrogen-like entity. So you have a positive ion, which replaces the nucleus of hydrogen. So you have that positive ion, and one extra electron, which in the language of Bohr's model, orbits around that positive ion, around that nucleus-like object. Right, the analogy with Bohr's hydrogen atom is clear, it's obvious, so we can directly use Niels Bohr's result for the binding energy to find the binding energy of our electron to the impurity ion. But we need to make two replacements in Niels Bohr's result. So replacement number one. Think about Coulomb's law. So the electron and the ion interact electrostatically through Coulomb force. Coulomb force tells you that is proportional to the product of the two charges, inversely proportional to the square of the distance, and this ratio, product of the charges divided by the distance of this distance squared, is multiplied with a constant called Coulomb's constant, Ke. But that's in vacuum only. In the medium, Coulomb's law needs to be modified. You need to divide the force by the electrostatic, by the dielectric permittivity of the medium, or also known as relative dielectric constant, permittivity, epsilon. So the reason for this extra parameter, permittivity epsilon, which is bigger than 1 strictly, it equals 1 in vacuum, but in all materials it is bigger than 1, so that the Coulomb force is weaker in a material, in a medium, than in vacuum. The reason for that is that the electric field produced by the two charges, Q1 and Q2, polarizes the atoms of the medium. And the atoms of the polarized atoms of the medium create own electric field, which gets superimposed on the electric field acting between the two charges. And this induced electric field always weakens the interaction between the two charges. It never strengthens that interaction. It always makes the Coulomb interaction weaker. All right, so the first replacement is to divide Coulomb's constant found in the expression for the binding energy of hydrogen atom, or ionization energy of hydrogen, or Rydberg's constant. Divide Coulomb's constant by the permittivity of the material. The second replacement is that the electron mass in this expression for binding energy must be replaced with effective electron mass, because the electron finds the whole system finds itself in a semiconductor, with bands and stuff. So the electron mass must be replaced with the effective electron mass. All right, so now let's look at the binding energy of the electron. For an electron in a hydrogen atom which finds itself in vacuum, the binding energy is the energy difference between the ground state of the electron in the hydrogen and the electron far away from the hydrogen in the state of at rest, right? So it is the minimal energy that you need to give that electron to remove it from the hydrogen atom, and when you do so, the electron is at rest, but it is not bound to the hydrogen atom anymore. Now, in a semiconductor, the binding energy, which is the donor, the ionization energy of the donor, is the minimal energy that you need to give an electron attached to the fifth electron attached to the donor atom to promote it from the donor atom to the to the very bottom of the conduction band. So as shown in this energy band diagram. So this is ED is the energy of the electron attached to the donor. And EDI is the energy difference between the bottom of the conduction band to the donor energy ED. So this is the donor ionization energy EDI. Now I have taken the expression for Rydberg's constant. I have replaced the electrostatic Coulomb's constant with Coulomb's constant divided by epsilon, the electric permittivity of the material. So here is my epsilon. Coulomb's constant is squared, so I need to introduce epsilon squared in the denominator. And I have put a star on top of the electron mass here. So we see that the result is practically the same as Rydberg constant, Rydberg energy, but with epsilon squared in the denominator. So it is 1 Rydberg divided by epsilon squared, and the electron mass is replaced with the effective mass. So if I multiply Rydberg constant with the ratio of the electron mass, effective electron mass to the free electron mass, and divide by epsilon squared, I will get the ionization energy of the donor atom. Now, the treatment of acceptors is similar. In an acceptor, in the neutral acceptor state, you can think of it as a negative ion with a hole orbiting around that ion. So you replace the electron with the hole. Acceptor ionization energy is the energy that you need to give that hole in order to promote it from the acceptor, from the bound state, the state in which it is bound to the acceptor, to the valence band. So it is the energy difference between the acceptor energy and the valence band energy. The acceptor level is close to the valence band. Otherwise, the treatment is the same. So again, you replace Coulomb's constant with the ratio of Coulomb's constant with to the electric permittivity of the semiconductor. So the electric permittivity in silicon is 11.7. Okay, so this number is of the order of 10. And also you replace the free electron mass in Rydberg's constant expression with the effective mass of a hole, M hole effective. So this is what you get. Now, in semiconductors, epsilon is of the order of 10, and let's assume for simplicity that the electron and hole effective masses are the same as the free electron mass. Then we see that the binding energy is about 100 times, should be about 100 times smaller than the ionization energy of hydrogen, which is 1 Rydberg. So 2 orders of magnitude. So 1 Rydberg is 13.605 electron volts. So the ionization energy of your impurity is only 0.14 electron volts, 0.136. But of course, it is actually a little bit less than that, because the effective mass of electrons and holes is typically smaller than the free electron mass. So the actual ionization energy is maybe twice as small, or 70% of this value, or something like that. All right. So we know the ionization energy of these impurities, and we see that it is only, what, 5 times, yes, about 5 times, 4 or 5 times higher than the thermal energy, 26 millielectron, so 0.026 electron volts. All right. So to figure out the impurity, the concentration of ionized impurities, we need to build a model. And here are the assumptions that our model is based on. the most drastic assumption is that we will neglect the ionized, we will neglect the excited states of the electron or hole in the donor or acceptor impurity. So the charge carrier can be either attached to an impurity, in which case it finds itself in the ground state, or it can be detached from the impurity, in which case it is free. It is either an electron in the conduction band or a hole in the valence band. Second, now impurity degeneracy. Okay, so this is not really an assumption. This is like a fact of life. Electrons attached to a donor impurity can be either spin up or spin down electrons. So the ground state of a donor impurity is has only spin degeneracy. Its degeneracy is 2. Now in silicon, the semiconductor that we always will be having in mind, the acceptor impurities have degeneracy 4. And the reason for that is that there are 2 types of holes. The heavy holes with smaller curvature of the energy versus momentum relation near the maximum, and the light holes where the curvature is large. So there are 2 types of holes. Each hole can be spin up or spin down, so that this gives you degeneracy 4. Now, this is actually the picture that I just made is not quite correct. There are some subtleties, because like if you talk about heavy and light holes, then the energy levels of the ionization energies for heavy and light holes must be different. But actually, no, they are both characterized by the same ionization energy, which is a little bit counterintuitive. But what happens here is that there is something like hybridization of quantum states. Like we have already discussed hybridization, sp3 hybridization, when silicon lattice is formed, when 1 s orbit and 3 p orbits hybridized into 4 sp3 hybrid orbits. So similarly, the quantum states corresponding to the heavy and the light branches of the energy momentum dispersion relation, they hybridize into a single state, which has into a single level, which has degeneracy 4. Okay. So therefore, heavy and light holes have the same binding energy to the host acceptor impurity atom. So this is good news, because life actually is simpler than we would expect naively. So the result of this hybridization of heavy and light holes, I mean, it was described something about like, it has been known for about 50 years. All right, so let's keep moving. So finally, we are able to answer the question, how many donor impurities are actually ionized, and how many acceptor impurities are actually ionized. So let us think about donors first. A donor can exist in in 3 states. Neutral donor, when an electron is bound to this donor atom, that electron can be either spin up or spin down. So neutral state is doubly degenerate, 2 states, right? And then ionized donor, which can be realized in only one way. We can think about the donor atom as the system in contact with the heat bath. And the heat bath is that sea of electrons, conduction electrons, which move around the semiconductor crystal. So that's your heat bath. So your system, your donor atom, can exchange particles with the heat bath. It does not exchange energy in the form of heat, because the donor atom is just a single entity. It is meaningless to try and introduce the thermal energy of a single atom or a single electron. All right. So we can apply the knowledge, what we have learned about the grand canonical distribution, to this system, to this donor atom. The probability to find the donor atom in the ionized state, that is to have 0 electrons attached to it, is just 1 divided by the partition function, grand canonical partition function. And the probability to find 1 electron, either spin up or spin down electron, attached to your donor atom is exponential to the power negative energy of that electron attached to the donor, ED, minus the Fermi energy divided by the thermal energy, KT, and this exponential is divided by the partition function Z, grand canonical partition function. So this partition function is found so as to, from the condition that the total probability must add up to 1. And the total probability is the probability of either of the one of the three outcomes. No electrons attached to the donor, spin up electron attached to the donor, spin down electron attached to the donor. So the degeneracy of the donor is 2 for spin up and spin down. So the partition function is 1, the numerator from here, plus 2, the degeneracy of the donor, GD, G sub D, times this exponential. Yeah. So now P0 plus P1 plus P1 add up to 1. Okay. Again, P1 enters twice because of spin up and spin down possibilities. So the probability for the donor to be ionized is the probability to have 0 electrons attached to the donor. So it is just 1 over Z. And it is given by this formula, right? The probability for a donor to be neutral is 1 minus the probability to be ionized. Or it is the probability to have 1 electron multiplied by 2, the degeneracy of the neutral state, the degeneracy of the neutral state. So in any case, it is 1 divided by 1 plus 1 over GED, donor degeneracy, exponential to the power E donor minus E Fermi over KT. Okay, so the probability to be ionized is of main interest to us, right? As for acceptors, so the treatment is fairly similar, except the degeneracy of acceptor is 4, not 2, it is 4. But here are the results for the, this is the result for the concentration of ionized acceptors. So similar treatment gives this result, and this is the result for the concentration of ionized donors. Now, an important conclusion can be drawn by just looking at this formula. We still do not know exactly these concentrations because we do not know the location of the Fermi energy. But if the Fermi energy is well inside the band gap, that is, if your donor level is, if it is an N-type semiconductor, and your donor level is higher than the Fermi energy by at least a few thermal energies, kT, then the exponential in the denominator of the first formula becomes negligibly small. If Fermi energy is smaller than donor energy, then exponential is raised to a large negative number, and it becomes small, much smaller than 1. That is, the concentration of ionized donors becomes pretty much the same as the total concentration of donors. And this is what is really typically found in doped semiconductors at temperatures close to the room temperature, in a large window of temperatures around room temperature. As for acceptors, notice that acceptor energy and the Fermi energy enter with opposite signs in the exponential in the denominator of this expression for the ionized acceptor concentration. See? Here we have, for donors, we have E Fermi minus E donor. For acceptors, we have E acceptor minus E Fermi. Now, you can think of that sign difference like holes can be viewed as anti-electrons, anti-particles in some sense, similar to how positrons are viewed as anti-electrons in free space. The energy of holes is measured downward. So the energy momentum curve in the valence band looks like this, like it is like an inverted parabola. But holes view this relation kind of inverted. They see it upside down. So the whole energy is, if you count the whole energy in the opposite direction, then this sign difference in the expression for the exponential of the exponential makes sense. All right, so now for acceptors, if the Fermi energy exceeds the acceptor energy EA by at least several thermal energies, then the argument of the exponential becomes, again, large and negative. The exponential becomes negligible, and the negligible as compared to 1 in the denominator. And so the concentration of ionized acceptors becomes about the same as the total concentration of acceptors. And of course, the concentration of neutral donors and neutral acceptors is the total concentration of impurities minus the concentration of ionized impurities. So that's that for today. Thank you all very much for your kind attention. I'll see you in the next lecture. Bye.